So my talk will be mainly actually going back to the just covering basically my career when I got introduced in 2000 basically to the neural networks. And since then I've been on various projects and various software. I've been going through the neural network projects, and that's why I wanted to just sum up the background, how in geophysics, what I see, or actually it's more my point of view, how it is applied in various aspects which I have been through. Although there are many other applications which I may not have used, and that would be open for discussion further things. So to start with, why neural network? Database are obsolete. So why artificial neural network? Because it is the basically what interpreters do, what humans do in perception. So people have been trying since the computer time to, one is the logical way of getting the math and the statistics and all that variable and regression. The other way is why if computer could learn. And that is the main thing, learning and perception, and getting the basically the idea from human brain is that it is robust, it's flexible, and it can work with inconsistent data. And that's what we deal every day. Like in geophysics, we deal with inconsistent data, noise, everything, and all the problems associated to which we can blame somebody else for. All those are come to the table, and you never have a perfect data, you never have a perfect what you wanted on the table, but you have to deal with it. And so handle unforeseen incidents. So the regressions and mathematical and quantitative may not be able to handle unforeseen incidents. And that's where large amount of data, and sometimes you don't have time to go through all the details which you wanted to go through, and it happens with every project. So getting the neural network to is to understand how the human brain works, and that's what people started doing with the networks. So research started back in 1943 when there were no computers, but McCullough and Pitts, they tried to find a logical function where you can memorize, or where you can actually have a learning experience. But the problem was they they could assign the weights, but the problem was that if they only could run linear algorithms, not the parallel algorithms, because there was no computer, there were linear various circuitry to get the linear information through, but not the parallel information. So that's so 1960s the research kind of stopped, and then the computers came in to help them recalculate some of these. So those algorithms came back, and especially one of the Rumelhart published for the nonlinear optimization. So nonlinear optimization, as you already know, that nonlinear have been introduced actually in inversion, it has been used in seismic inversion, and various other quantitative methods. But the nonlinear helps to get the neural networks back to the optimization. So the major difference, and we will see what it is different from statistics in the neural network domain. And in 1990s, there was a huge push in the software industry getting that all algorithms back into the real application in geophysics. But let's go back to the real what it is. Uh, Starting with the various applications, right now what you see is in the Google search and various of the Facebook relation search and various, they are putting a lot of effort to getting from the YouTube, getting the cats out of the YouTube videos. Like you've heard all those neural network algorithms to try to get the things out when you're not very clear about what they're really quantitative. Like there's human perception. It's the same. Like I recognize many faces. Half of them I don't remember the name, but I still recognize them because I know where I met them and those things. Because all these are built into my neurons to get that perception, or at least I have some relationships related to some company or some that, So I would go back and 10 years, okay, 10 years back, I saw West 10 years back presenting SciSex. So it was one of the methods. So it is all the perception, and that is the built-in into the human brain development over the last 200 million years is the development through these. So it is really, really very complex. So you would never be able to mimic the human brain. But there are certain qualities you can introduce into the algorithm. And so, so the basically the learning is the key. So learning. So if computers can learn, is not only crunching the numbers, but actually programmed to crunch the numbers, but actually can learn. And that was the key in the elements in the neural network, was that the processing element, you have input layer and then a hidden layer. So now you basically, if you do a single functions of all the processing element and come up with the output layer, that would be called the statistical analysis, or could be called principal component analysis, to coming down from a full input elements into a one or two output elements, or whatever you're looking for, like an inversion. But that's where the neural network comes in, is the hidden layer. Now this hidden layer have all the relationship back to the processing element, and it have connection weights to the output layer. So what it does, what you benefit from, that hidden layer is the only nodes. They are interrogating the rest of the functions, and they're only changing the weight here. So on the next layer. So you are actually basically not going back to the data every time you need an answer. You are not opening 20 volumes to tell what the weight is. You are actually changing the weight based on if that function worked. So the between hidden layer and the data, if the function worked, or certain threshold, and that's what the brain threshold, at certain threshold, if it worked, it will change the weight. And they only have to deal with the rest of the few pieces. So it doesn't have to deal with all the rest of the data. So every node can work parallel to each other. And so now you have millions of nodes working separately, and then coming to the second layer and to the third layer. So you have multi-layer perception. So each layer has its perception. It changes the weights to the next layer, and it changes the weights to the next layer. So now you have each layer starts with a random number and then goes on to the next layer. So you get a perception following through. But this is supervised. Supervised means you know the answer. Kind of you are giving it the answer. So the other application came actually, that was Conan SOM, self-organizing maps, when you don't know the answer. Well, you don't really know the answer, but you know that these data are related, or these data sets are related to certain answer. Like your main data, which means inversion or just the wiggle trace, they are related to some geology. And now they are wavelet, they have all other things, but they are related to geology. So you don't know the answer, but you can try to use the data by itself to speak for it. Of course, you have to put some constraint that what functions you can really applicable. So you have to put the constraints of the interval and certain things. So that is where the two segments of the neural network application, and again, Kurt Marquardt and those have explained very well with all those details, and those who know the writing algorithms and user side of it. So I want to bring in the things, how they are used rather than how they do it, because I don't know all how they do it. So why use neural network in reservoir characterization? So that's the most important. Why we need another tool or another things to use is that because seismic attributes alone cannot identify. Single attribute by itself sometimes do not relate to the geology by itself, or to the porosity by itself, or one single attribute. So, but all those together, it's like human as a group together can do a lot of miracles, but a person, a single one cannot do, because everyone have a limitation. But you overcome the limitations by grouping various attributes together. So any one single attribute could be completely noisy or being not really giving the answer, but as a total at the end, you might have a combined feature can be detected by multiple attributes. So seismic attribute may reveal some of the target features, but not all. But so quantitative information to geology, it may be very skewed link, and you could not see it directly from the inversion. You could not see certain things from the seismic data by itself with wavelets and everything. You may not be able to see certain things. So in order to put it all together, the neural networks are there to help getting back to the nest, to convert them into geology. And so again, the large data set has been always the problem, because you get multiple attributes and then you don't know which one to use and how to use them, and then get all of those interesting. And that's where you come into the next level and say, I will only use the one I know. And so you might be missing the things which you certain attributes you might be completely miss in the workflow. So I will go through the examples, and it would cover the one software which I have used in the past or I have experience with. Although could be many other applications which would have implementation. So neural network, just going back to the history, I don't want it to put exactly because I don't know exact dates when they started, but the first of the original was Stratomatic and neural network application from DGB back in 1995. One was Dutch, one was France. They started doing some of the research, and that was 98, was the first applications came out in 1998. I know you can correct me if Hampton Russell was there almost at 2000. They started putting in the new algorithm for the porosity inversion, from inversion taking from inversion. Same as paradigm started with the Vanguard, which was also the neural network inversion. So what both things were doing, the Stratomatic and neural network plugin from DGB, they were unsupervised, and then Vanguard and Emerge were supervised neural networks. So supervised neural network were the extension to inversion, because inversion you get results. So the extension to inversion is that you have very close results to porosity, or pre-stack inversion to the water saturation or the fluids. So you can actually make them convert into porosity or gamma ray volume or V-shell volume or various saturation volumes. So that was the connection. But the so Stratomatic and neural network with the unsupervised neural network were completely newer area where you had no prior coming in. So that was so I will go over the examples from UBQ or Conan SOM, unsupervised neural networks, and then I will show you the supervised neural network, what applications, what I know of exist at this point. So this is basically the talk is all about the examples, just showing what I have or the ones which I could show. So basic, so unsupervised neural network. So starting with unsupervised, you have, this works just like an interpreter. If your interpreter is looking for the changes in the waveform as you are down to one horizon, trying to find out the waveform shapes and changes, and then you go back and forth. It was working fine with 2D. Sometimes you do area under peak, area under trough, peak to trough ratio, peak to trough distance, amplitudes, all of those attributes. You do it on the workstation, calculate sometime in the notebook, sometime actually on the screen, sometime on the map. But basically, the idea was to quantify them or actually qualify them with a neural network. So taking the interval, you could take the interval and put the input as that interval, all the traces within the specific interval. It's still I wouldn't say it's fully unsupervised. It's still supervised by your horizon and by your interval. That's the user input. And then you're actually giving it to go over the synapses, so change the weights and those and come with the classification. So the classification, what was the unsupervised reason that it have to be different enough from each other, but they have to be somewhere in the sequence. So the sequence was really important. Like the waveform have to come in a sequence. If you're looking on a wedge, it has to go through in a sequence of changes. And all those sequence of changes are buried into these. So the classes have the interrelationship. And that's what one thing about Cohen and self-organizing maps, but because it's called self-organizing maps, because it's projected into a space. So multivariate space is projected into a single space where you can project into a series of points. So you're actually minimizing the data by creating models. Now, any one model is not fully related to back to the any seismic point, any seismic trace, because you're not taking a trace and looking for it. You're creating a model which is the center of the class or center of the cluster, you can say. I avoid using cluster for neural network because just basically cluster analysis confuses between the actually clustering versus sometimes actually same cluster might have more than one classes in the neural network domain. And so there is multivariate clustering is something which is more of the technology. So coming with Kolu with Manuel Pupan and Kosias have presented a paper back for the Indonesia, one of the Indonesia offshore data set, that you can start seeing the channel. Of course, when you mark it, it looks very nice as well as the faces changes. But what they showed is actually one more, that if you change use the principal component analysis in combination with neural network, you're going to get even better results. Because now you are bringing up geology. Now, all of a sudden, you are looking at an amplitude map, which you might be able to see this portion, but now you're coming into a called facies map. That's why they call it seismic facies, like starting with neural network application or all seismic facies related. That see your channel, if you just go back and forth, the channel which would have been picked like here, but you couldn't judge it from this map, would be start seeing going a full change in the strike slip fault. So you're actually looking at the strike slip fault, which is displacing the channel. Why it is important? Like because facies, when you're putting a facies map, you're actually making sure your interpretation is following the geology. And that is the every software is trying to do is to slice through the geology rather than slice through the data. And once you put the facies together, then say, okay, if geology is following this, it means I am on a close to a flooding plain or some area. But it is very important to have the don't go into the horizon. Like if you are going into the geology, you cannot see the geology. It's like going into the woods and you cannot see the forest because it's just the trees. So if you get into the traces, which means if you're micro guiding from your wells and other things, then you don't see the picture. So you have to get a horizon which is easy to pick. And that's what I always sometimes say. I am the laziest one because I didn't go through the interpretation all detail. Just took one of the easy pick horizon and then go to the intervals. Because that's the idea is the data would speak more if you are outside the actually looking at the data. Because when you're picking, you actually have your model in mind and your own neural network is taking over. So you're not letting the other neural network do the job because your neural network is much stronger and actually it's much better. So you can actually, but it's only limited to certain small synapses. And so the other paper actually got published with the integration of all the neural networks versus the amplitude analysis. And so you see the inversion output and the various parameters, but once you put the facies together, and in the facies you can use more than one input. So it was basically used as the impedance as input and amplitude as input. So you can actually use more than one input. But using seismic or its derivative like polarity and those would not help because they are derived from the same attributes. So it would be like inversion would be a different attribute, or similarity and those other things would be a different tool coming into the neural network. So, yeah, from that example, going one of the close to home example of the carbonates, like just the carbonates taking unconformity in the carbonate, in the Mississippian unconformity, you could actually quite closely pinpoint the unconformity area, the erodic surface with the porosity. So if you look closely, this is the interval, but it is picked just on the top, the trough, which is able to pick. But you could not, you can pick it through, but the amplitudes will be away from the unconformity or inside the unconformity will be the same. So that is why if you keep away, you are putting in your time difference for the unconformity as a part of your attribute. So that's where uh, so coming a very good example like come from the deep basin is that you're coming looking at the Nautikian channel system, but you see this meandering bath. Now, of course, we say, okay, yeah, well, this well and this well were closely placed, but this also can tell you from the well, because if you have such a clarity and with extensive number of wells, you can look at a well and start actually saying where that channel coming from, because you can use the geological now more information from geology to start looking at the meandering and the bar, and maybe able some wells may be able to target a specific bar rather than, so you're targeting geology more closely. And we have liberty here, like all in the Canada, US, and many. There's extensive number of wells to control over the geology. So the neural network inversion as well as these methods are really very applicable because you anyway have few wells going through that geology to confirm. And it also could confirm if your migration operator is right, like if it's moving the channel back and forth. So it's not only that you bring out the geology, but if it doesn't come out, you can find the reasons why it's not coming out, or difference between one type of migration versus the other, versus the wind filling and those things. If these things get distorted, you get to see more. So yeah, this was actually a couple of papers we published on the cardium shore phase. By mapping a cardium isopack on the left side, that is looks at the changes in the thickness of the cardium, main cardium phase, and when you run the neural network facial analysis, you start seeing actually this was the main lagunal, or your thin is related to this thin. Now, if you look at this total, these are 20-meter thickness or 24-meter thickness, with in between it's about 11 to 12-meter thickness. So what happens in the frequency? You are getting into the tuning. So your tuning effect actually taking over the amplitudes, then your target is not deep enough. There are various other amplitude effects, like this is one of the surface related amplitude effects. So the amplitude effects, you cannot see past them. So you bring up the amplitude, oh, I can't see anything, so just pass on to the next. So by investigating through these, the geology really tells itself, because that one or two wells which were thicker in the geology, those were right here on the shore face. So your shore face sand, which was only 100-meter thick, was showed up here as a single linear, but when you're trying to map it, you would have a difficult time mapping it because you have a gas masking as well as your oil and gas and water, all levels are coming into that shore face. So that study is like once we did go through that study. Now you can extend that two-dimensional or map-based, based on interval neural network analysis into 3 dimensions by
using what called the unsupervised neural network, but it's still categorizing in a volume base. Now it's slightly different application because it's not a vector relationship. It's actually point-to-point multi-attribute relationship. But still, your input data is slightly different, not the wave shape, but actually the points. And but your output is that you can investigate. This was one paper, very nice paper published by uh, uh, mainly, yeah, published for the turbidites or actually the main flow. So if you can actually offshore data, you can find out the flow environment by using the attributes from the seismic. So you're basically doing it. You still have to figure out what is inside and which part of the turbidite. You still have to interpret above and below to constrain your neural networks, but it's mainly unsupervised application. So then I go to supervised application because these were the unsupervised. Now supervised network have a lot of success or a lot of questions by itself because it depends on data to data. Your constraint or you see the examples from certain data, and in the foreland basin, like you don't see the chimney in the soil in the other than Gulf of Mexico, you don't see the salt bodies, and so various places you go, there is a different geological setting. So when studies are published, you have to be, if it's not related to, you think, okay, yeah, well, it may be applied there, it may not apply here. So, but the network is the same. So neural networks is the basically looking at all the attributes, trying to create a hybrid attribute or meta attribute which would work to specific task for you. So that so examples are like very simple. That pick an example, take the seismic data, define the attribute set. So these are two most actually important things. Pick the examples. So you can use well data or you can use the seismic data to pick the example. So you say, okay, I interpret this to be chimney or I interpret this to be salt body, then that is my sample. And the other thing is that you can say these are, or I can want to pick the faults. I pick few faults and I give it that, okay, these are faults, these are not faults. You go and look for them. So then you define the attributes which are related to the fault. That's the most important in any successful project in neural network. The most important that you know that those attributes are related to the one task you want to do. Of course, computer can help, but it's always the interpreter who is in the driving seat. Like it's always you can get the best car, but if you don't know how to drive, it's not gonna. I still can't drive standard car, and so I can have the best car, but I can't just change the gear in time. So that is what it is. Driving seat is still the interpreter. So what like there's some of the examples which were initially applied again going back to late 1990s or early 2000. The main thing using well data to take the input from the reflectivity, acoustic impedance, elastic impedance, come up with the porosity, and then from porosity, using porosity as an attribute, come up with the water saturation or variations within water. This was one of the 4D study which was published about in 2000, 2001. But this is one from Hanson Russell. Like some of the how the emerge chain could actually pinpoint better porosity from the inversion results. So better than the regression. So multi-attribute regression was before neural network being applied heavily. But you're always comparing what you can improve, and I think neural network have shown over the past 5 to 10 years that it can do better job. Uh, the only, and I was talking before, the only thing is that new algorithms are not yet incorporated into the oil and gas industry, and which is very need to we need to go back and see what have progressed in the neural networks, and then we bring them back. And I'm sure many of the academia and the software companies are doing that, but I just didn't see products yet which are using advanced neural networks. So the looking at the one of the example, this was from by Timothy Bird, one of the paper, which he showed that how it really improved. If you look at the structure, you would never drill a Y1 well. But if you look at the attributes, using input attributes as uh, mainly your fluid marker attributes. So this well which was wet and this well which is drilled on the other side of the structural plate was basically based on these attributes. And that would be that using neural networks you could narrow down, one is the porosity and the water saturations from your multi-attribute, like from your inversion, simultaneous inversion, or various inversion methods. So now we are bringing in more from the not only post-stat seismic, but you're bringing in already derived quantitative attributes into your neural network, and that is becomes very important. But now I just want to go through this one is basically how you train neural network, like specifically for a certain task. One of the 3D, you say, okay, well, I see something vertically aligned, and which is the people who work with the chimney quite a bit know that, okay, vertical aligning changes may be related to a chimney attribute. So you say, okay, vertically, this is the green one is my chimney. I say, okay, yes, that was the chimney. And I say, okay, I don't see any vertical discontinuities, and so it might be non-chimney. So I gave it two sets to work with. So what it did, and then I asked it to, because the inertia changes, similarity changes, local dip changes at the points where I want to see, and the points where there's no chimney. Now, on both those points, now I'm just trying to train a neural network. Now, the training part is quite feed calculated data to neural network. So neural network will find at every blue dot, I have these attributes, like this set of vectors. And then on green side, I have these. Now, if I can differentiate between these two, I will create a probability or weight function, because I remember we are just changing the weights of the hidden layer to the final layer. So you are actually saying, okay, well, if I change this weight, this might similarity have a highest effect on this output. So I would change the weight to be highest to the similarity. So you keep on changing the weights till you get the best function. But it's not a single function which is defining. So what regression and statistics does is a single function or a multivariate function. In this case, you are actually just does not allow any function come into place. The function role is to change the weights. Its role is not to guide it directly the result. So you are actually putting intermediate layers to guide it better. That's what difference between neural network and the normal regression or finding the relationship. So the what you end up is the apply neural network, and then you get the probability of being what you picked. They say probability of this is also here. What you have picked or asked me to pick is also possibly here. This one of the fault might be leaking, or what they did, and it's a lot of research from Statoil and these, and I have few examples from their published paper, like from the Hagland from Statoil, that you start building your subsurface model. You start building your geology, your fluids, and everything. And chimney is the one who could connect that, especially for North Sea, Gulf of Mexico, and very many rift basins in the world. It could connect the salt dome. Like salt dome is also through same process. You can select the salt dome and like its attributes. Then deep reservoir, the chimney by itself, then coming to the shallow reservoir, and you start seeing on the paleo mud flows, like the similar to the mud flows, you can see on the paleo structures where you have the paleo flows within your fixed horizon. So you sometimes have the pock marks in the paleo, and and also surface expression of the seepages. So you're now actually tying all the hydrocarbon system coming from the flanks of the salt with the salt push all the way up to which horizon would be leaking. See this leaks, individual leaks of these horizons. So if you're drilling to the targets, various targets, you need to know where the leaking and where it's non-leaking. So that's the other what we found is that over the big oil fields, there are gas clouds, which mean the hydrocarbon still leaks through the seal and creates the clouds, which means clouds your data by hydrocarbon migration. What happens is the chimney is just a small micro AVO attributes. So it's actually every point where the chimney is, it's just distorting your gathers so much based on the AVO effects that you're not getting the data through, because you cannot fix it because it's just hydrocarbon have created a saturation level. And there are last couple of years there are very good studies offshore from New Zealand showing how it is modeled and how it is done. So, and the other is like you can understand the fault cube and then tell which faults are leaking and which faults are not. That would be Lichtenberg study from this was showing. So now faults can be the same process goes for fault, same process goes for chimney. But the only thing is the faults you are giving different attributes and you're not looking for vertical migration, while in chimney you're looking for vertical. So you're saying, okay, if this attribute exists 100 millisecond above this would exist the same attribute 100 millisecond below. So it have a vertical alignment. If it doesn't have vertical alignment, that would be thrown up as a noise and non-chimney. So you're actually reducing your data to your needs, and that's where you come in, like leakage at fault intersection, certain places, and certain with no leakage. So sealing faults, where your prospects would be if it's sealing or leaking. Like the same with the Lichtenberg, again the same in Gulf of Mexico, the study showing how the faults really migration happens through the faults, and they see this on the surface expression of the faults. You see the pock marks lining up with the faults. It's more like recent how things are moving. So it is no longer just a cliche like we have the chimney as a part. Of course, there is still within the practice of chimney analysis, you can be misguided because you are the input. Like as the interpreter, you can be end up with non-chimney, the look-like chimney because the attribute selection and the selection of your supervision. Because it is all what you're supervising will show up as the results. So the main like a leakage through the fault system, and this is one of the study we did in Newfoundland, offshore Newfoundland in the area, and you can see the Ordovician main Ordovician limestones are actually there was on the 3D you could see the chimney all the way coming to the surface. You can see a little bit more and it coming to the below the subsurface. There are various studies in offshore Newfoundland on the western Newfoundland which have shown the pock marks and those related to this. So you have a various system. Now again, means if you look at this one versus this one is not that real because it's a thrusting. So you have extensive faulting, and that could affect your chimney effects. So I at the end, I just want to go over one exploration application because we started with a very supervised, unsupervised. The idea is how to use it in exploration, and that is where we started about about 3 years ago, working with a very nice company from Kenya, exploring in South Hamza Basin. So what we did is a bunch of 2D lines. So it applies on the 2D and 3D. So what we did is that go over the multiple 2D lines. Original wells were drilled like this, Anza well and the Bahati well, which is drilled here, and the Andela well, which is drilled in the center. So this basin outline, we started seeing if go over the 2D chimney analysis or neural network analysis, we end up seeing the high leakage on this system, or especially the highs. So all of the exploration effort was focused on the highs because you want to drill a structural high, but the failure would ascertain to be more higher risk than the areas with lower this. So if you look at the line with one of the 2D line, which is one of the regional, you see a lot of leakage, and there are certain way to telling if the leakage is related, because near surface you get a high amplitude anomalies, you get various effects. This is onshore data, so you can't get the pop marks and those things, but if geochemical survey can tell if there are high leakage in one area than the other. Then a smaller leakage in this area. So you're looking that line closely, we figure out that the actual maturation would have happened deep in the basin, and then it doesn't migrate vertically because you have a lot of mudstone sitting in the middle but it goes caveate on both sides. But as it progresses, you have sands coming in from the west, and then that's where we recommended to go to the next level and shoot a 3D on that limb on one side. So coming to the 3D, I think I just went too far. So we did the fault kind of what's called the neural network fault interpretation. So these are the neural network fault results, and looking at the automatically going. sorry about that. So the like these are the individual fault traces. So the complexity, there was really high complexity of fault. So just one. So coming, okay, that's. So then we did like the fault analysis, then overlay with the chimney analysis. So what in the chimney analysis, what we will see now, the lower system where the main possible origin of the source rock would be migrating here, and some of the main faults are going to be leaking versus smaller faults in the vicinity would be non-leaking. So you can tell the difference in the seismic signature and then can separate them to be non-leaking versus leaking fault. And that would be a lot of work to see individually, go through all the faults and say if there are fault gouges there and is it migration fully happen. So you go and train one and then you go through fault and chimney cube. Putting that together, go back. So go slice by slice. If we're coming from 2400 millisecond, you see the basin side is this way, and coming to the these, I know it's then you go to 2200 millisecond, and you see the chimneys, more gas leakage would be these fault, and then coming up on the top, like coming to the 2000 millisecond, you see these further getting fed. So you are actually, the migration is happening from the deeper to, when you slice through, you can see the migration effect. And then you, on the top, you bring in the unsupervised facies, which is your, so again, there is no well in this area, and it's still rig is standing there in one of the spots. But the one now, if you go through the individual horizons and go through the facies or neural network way of facies, you see now these are very interesting, probably growth sands on the lower side at the CAN 100 level, or then as you go up, the colors you don't have control because neural network sometimes gets the color. So you see the sands are now changing more to these, a possible sand play at 110, and as you go further up, now your sand prone is changed. So you're actually having a sand influx into the fault plane, and it is changing as you go up the system. So you have to find the right migration place and the right sand place before they get too much leaky, or it is quite a bit relationship between good sand and then also a good neural network application. So the idea was to bring like from neural network application from all the way from a very highly we can say development valves to the all the way in different parts of the world. We are like going through the rift system, because rift system is a leaky system. So in order to, if anything can help to reduce the risk of the leakage of the faults, that would be these neural network can bring. And in the case here, you have the development decisions like in heavy oil and these things, the porosity. If you can get to the right porosity, or if you can get to the right parameters within the shale and sand. And Kurt Marquardt actually very well explained some of the applications that how you can get to the best sweet spot. So all these applications is only evolving based on the interpreters like you. When I won't put myself in the interpreter, and always learning from you and helping one step what I can bring in. But that's the idea, is how to get these available for the geophysical community, these tools, to bring it to closer to the answer. But you will never have all the data available. You will never have full interpretation, and you always have to make decisions with 50% and with limited knowledge. So that's where one thing I want to thank, the special thanks to Kohanan, who started all this neural network research, and he is still actually still publishing paper. The last time I saw is 79-year-old. So, but he's from Finland originally. Kohanan is very. It's called Kohanan Self-Organizing Maps, which is neural network. And again, thanks for CSEG for providing this venue, as well as thanks to Pulse and Absolute Imaging for providing some of the data sets, and Vanoil for letting us study DGB Earth Sciences for software, and also again help in that, and Petro Explorers team, Valentina, Rashid, and me, like Petro Explorer team, just far on the back. Thank you very much all, and
quick question. When I've played with neural networks, one thing I find is a key parameter that's tough to get a handle on to begin with is the number of nodes that you're going to put in your in your intermediate layer and then in the final layer. Do you have
it is.
thoughts on how to...
Well, if you are on that level, I would not be the right person to ask because of these. But the input, like the how it is implemented in the software, it all depends on software to software. How it is implemented. Some are very clear with no hard to, you don't have too many choices to make, and sometimes you have a full control on it. So it's all the learning. Actually, it's human learning as well, how to use it based on the nodes. For the facies analysis, I can say that you number of choices of the wavelet, if you mean by the wavelet choices, like how many you go and how big the wavelet you go. Usually it is which can cover your geology, but it's more than one peak and trough. One peak and trough or one full wavelet to be at least used. But because you have side lobes and those things, it's better to use a little bit bigger wavelet for first analysis and then focus into the next wavelet level. So it is always a sequence on multiple tries to what works, what not, or you can change your. It's always better to change your input horizon, like what is your focus horizon, your interval. So you have to change either top if you're using, like say if you're looking for an unconformity, it's if it is not fully covered by a shale zone, you rather pick it something continuous surface below and then use that interval. If it is covered with a flooding surface or a very good shale, then you pick the shale and then looking for that unconformity changes. So, and the number, it was I started with the rule of thumb, and then, but pretty much now 10 to 12 classes usually cover most of the uh, unsupervised classification, like 10 to 12 classes. The nodes in the other, I don't know if specifically which software you were pertaining to, but there are different systems have different. So node layers is actually your 20% of the data you should keep as the test data. Like if you're inputting, and your input data have to be bigger volume, because that's the key always comes in. I will try it on a smaller piece. There's actually neural network need a lot more data than your smaller piece. So the number of traces and the number of input, you always have to keep in mind that neural network will not function good with a smaller number of inputs. That's why it needs a larger number of inputs. Either you do it through interpolation or through various levels. You have to give it higher number of inputs. And that's why I always people say, okay, why can't I run it on the multiple 2D lines as a interval analysis? Because you don't have enough traces covering that variation, like that specific variation. So it's all depends on data to data how you can get back.
One of the questions that I've gotten a lot over the years is how to quantify that. And one of the answers is just forward modeling, for wedge modeling,
Yeah.
for varying properties from one side to another, using that instead of doing the neural networks to derive the classes. Do you have any other experience on how you actually assign quantitative values to
Actually, that's very interesting. That I've been asked me, of course, the same question in the last 13 years. So, but the same thing, you don't quantify, because you have quantifiers which are actually bringing in. You understand from the data, and then you take whole as a class. So you're not further quantify, like means you understand the correlation within the class. That's very important. That okay, you can correlate within the class. Actually, the Manuel Foucault's paper did quantify. Eventually, did go into the next model type of and quantify. But again, we are coming down to the well situation because you don't have the relationship. Well is the most difficult to quantify because it doesn't have a spatial position. Seismic have a spatial position, but it doesn't have the vertical resolution. Well have vertical resolution, but it doesn't have the spatial resolution. So what happens in that shore phase on the Cardium, that you end up next well, just next to it is actually in the shale. And so you have a 20-meter difference. How you explain that only on the seismic? So you bring it, take the qualitative information as a site, because this is my geological scenario or information, and then work with quantifiers separate. Don't try to use the qualitative into the quantitative, trying to quantify the qualitative, because its neural network is coming with the qualifier, and the qualifier is this class versus this class. Once you start seeing the geology, then you use inversion method and use the supervised neural networks to come up with the supervision of those classes. Because if you're trying to use the waveform, it reached its limit in classifying. Because you're not trying to when you try to overdo, and that's what I did quite few next model related projects, but you always end up not understanding. So kind of undoing your understanding of the quality of the geology, because you reach the limit with one attribute. That's why it's always nice to work with various like inversion, AVO all together. Like all of these have to be in one workstation. And that's what really difficult for to getting all of these into one workstation, because then you can quantify. But qualitative interpretation is still, geology is qualitative, because you see things, you see geomorphology. Can you quantify geomorphology or paleodirections? Yes, you can say, okay, well, this meandering channel would have moved from this side to this side, or the water flow was there. But there are so many other processes which have actually destroyed that fabric completely, where it may be backflowed into that meandering channel, so you might have a filling and which covered it up. So there's a lot of variations, but it's actually very good to use the quantitative in addition to the qualitative. So you always work hand in hand, because your inversion results sometimes are not correct, but you think they are correct, because if you put a qualitative next to it, then you say, okay, it doesn't fit my geology, how my model, how it is going. So either this is wrong. So working together rather than trying to use the qualitative converting into quantitative.